Welcome to this session on Measurement System Analysis, or MSA. In this module, we'll explore the concept of MSA in detail, including its application to both continuous and discrete data. MSA is a critical part of quality management and Six Sigma, as it helps us evaluate how much variation in our measurement system comes from the measurement process itself, rather than from the actual parts or process. We'll discuss the types of measurement system errors, such as bias, linearity, repeatability, and reproducibility. And importantly, we'll also cover how MSA is applied to discrete or attribute data, where measurements are based on categories or classifications instead of numerical values. By the end of this session, you'll have a solid understanding of how to assess the reliability and accuracy of your measurement systems in both continuous and discrete contexts. In Lean Six Sigma, we start with this mindset. All measurements have some error. Nothing is 100% accurate. There's always some noise or imperfection. As Six Sigma practitioners, our job is to ask, is the measurement error big enough to affect decisions? If the error is too large, we can't trust the data. That's why we use measurement system analysis to check if our data is reliable. Let's say you measure a process and get 14.157385921035694 seconds, but you report it as 14 seconds. Technically, that's incorrect. It's rounded. But the real question is, does the rounding matter? In high-precision industries like microchip production, even tiny differences count. In everyday cases, like measuring lunch queue time, they usually don't. The key is, we're not chasing perfection. We're judging whether the error affects the process or the customer. Every business process shows natural variation. That's normal and expected. But when we measure it, the measurement system can add its own variation, creating error. Here's the key formula. Observed variation equals true process variation plus measurement system error. So, what we see isn't just the process, it's the process plus noise from the measurement tool. If the measurement system adds too much error, it hides the real performance of the process. Our goal is to minimize that gap, so we can trust the data and make accurate decisions. The purpose of MSA is simple but critical. We want to know how much of the variation we see is real and how much is just measurement error. If you skip MSA, you risk solving the wrong problem, fixing a process that's not actually broken, just poorly measured. MSA helps us identify measurement system error, separate it from true process variation, and decide if the measurement system is reliable enough to base decisions on. In short, MSA ensures we're working with trustworthy data. Think of this like looking through blurry glasses. What you see isn't exactly what's there. Every measurement includes two types of variation: true process variation, actual differences in the product or process; measurement system variation, error caused by the tool, the operator, the method, or the environment. Until you clean the lenses by improving the measurement system, you can't confidently act on what you see. That's why identifying and minimizing measurement error is so important. This slide outlines key best practices when working with data in any process, improvement, or quality project. The first principle is to be skeptical of all data until it is validated. Don't take numbers at face value. As practitioners, we must always question the source and accuracy of the data. Ask critical questions such as, how was this data collected? Was the measurement system evaluated through MSA? What is the margin of error? If someone presents a report or chart that didn't consider MSA, be cautious, because decisions based on unreliable data can lead to incorrect conclusions. Remember this key quote: you cannot improve what you cannot measure reliably. Without a trustworthy measurement system, process improvements will be built on shaky ground. This slide gives us a quick refresher on key terms related to measurement system analysis, or MSA. MSA stands for Measurement System Analysis, which is the overall process used to assess the accuracy and reliability of data collection. A measurement system includes the tools, people, and methods used to collect data. If any of these components are weak, the data becomes unreliable. Gauge R&R stands for Gauge Repeatability and Reproducibility. It's a specific type of MSA used to understand how much variation is due to the measurement system, both from the same person, repeatability, and between different people, reproducibility. And lastly, the term measure here refers to the act of counting, classifying, or making a decision based on data. Understanding these foundational terms ensures we're all speaking the same language when evaluating or improving our measurement systems. This slide explains repeatability, which is one of the two key components of Gauge R&R. Repeatability refers to the variation in measurements when the same person uses the same tool on the same part, multiple times. It's also called intra-operator variation because the same operator is involved in each measurement. The idea is simple. If an inspector measures the same item multiple times, the values should be very close together. The less variation, the better the repeatability. For example, if an inspector measures the diameter of a bolt 5 times and the values are nearly identical, we can say that the measurement system has good repeatability. This helps us trust that the measurement system is consistent when operated by the same person. Now let's look at reproducibility, which is the second key component of Gauge R&R. Reproducibility measures the variation in measurements when different people or even different tools are used to measure the same item. This is often referred to as inter-operator variation. So, unlike repeatability, which focuses on one person repeating a task, reproducibility involves a change in operator or equipment while keeping the part being measured constant. If different inspectors measure the same item and get similar results, it means the measurement system has high reproducibility. But if there's a lot of variation between their results, we might question the reliability of the measurement process. For example, if Inspector A and Inspector B both measure the same bolt and get very close values, that's a sign of good reproducibility. Remember, the smaller the variation across people or tools, the better the reproducibility. In this slide, we shift our focus to measurement system analysis for discrete data, also known as Attribute Agreement Analysis, or Attribute Gauge R&R. This type of MSA is used when we're dealing with categorical or count data, such as pass-fail results, defect categories, or ratings. These are not continuous measurements, but rather classifications. It still looks at repeatability and reproducibility, but in terms of how consistently decisions are made. Repeatability here refers to whether one person classifies or rates the same item the same way multiple times. Reproducibility refers to whether different people classify or rate the same item consistently. The main goal is to determine if multiple people make consistent decisions on the same items. If not, we may need to clarify the criteria or improve training to reduce subjectivity in decision-making. This is especially critical in inspection processes, audits, or any scenario involving human judgment. This slide explores the concept of effectiveness in attribute gauge R&R. Effectiveness refers to the level of agreement among repeated ratings or decisions for the same set of samples. The critical question we ask is, are appraisers agreeing with themselves and with each other? Let's look at an example. Imagine a textile company where 4 appraisers rate the print quality of 10 fabric samples on a scale of 1 to 5. Each appraiser evaluates each sample twice, and the order of presentation is randomized. We then assess how consistent the appraisers are both within themselves, repeatability, and across each other. Reproducibility. In this case, 8 out of the 10 samples had consistent ratings across all evaluations, which means the effectiveness is 80%. A commonly recommended sample size for attribute agreement analysis is at least 60 observations to achieve statistical reliability. Remember, higher effectiveness equals a better, more reliable measurement system. If the effectiveness is low, we might need to improve appraiser training or clarify the criteria for judgment. This slide introduces the concept of efficiency in attribute R and R, which is a measure of how well appraisers agree with a known master standard, not just with themselves or each other. Think of it this way. It's not enough to simply be consistent. We must also be correct. The key question is, do our ratings match the correct or gold standard answer? Let's look at the example provided. A textile company has appraisers rating samples, and there's a known correct or gold standard rating for each one. If 8 out of 10 ratings match this standard, then the efficiency is 80%. This tells us how accurate our measurement system is, not just how consistent. And remember, the larger the sample size, the more confident we can be in these efficiency results. So, efficiency helps close the loop in attribute agreement analysis by ensuring that we're not just agreeing, but agreeing with what's right. This slide addresses a common question. How much agreement is considered acceptable in attribute measurement systems? The truth is, there is no fixed universal benchmark. The acceptable level of agreement depends on 3 key factors: the risk of error in the process, the cost of making a mistake, and the impact on the customer. Let's consider an example. If you're dealing with high-stakes decisions, like in medical diagnostics, even a small error could have serious consequences. In such cases, we aim for very high agreement, typically above 90%. But in lower-risk environments, like routine inspections where errors don't have major consequences, an agreement of 80% might be acceptable. So, the target agreement should be aligned with the criticality of the decision being made. Key takeaway: the higher the risk, the higher the required agreement. This slide introduces the concept of efficiency in attribute R and R, which is a measure of how well appraisers agree with a known master standard, not just with themselves or each other. Think of it this way. It's not enough to simply be consistent. We must also be correct. The key question is, do our ratings match the correct or gold standard answer? Let's look at the example provided. A textile company has appraisers rating samples, and there's a known correct or gold standard rating for each one. If 8 out of 10 ratings match this standard, then the efficiency is 80%. This tells us how accurate our measurement system is, not just how consistent. And remember, the larger the sample size, the more confident we can be in these efficiency results. So, efficiency helps close the loop in attribute agreement analysis by ensuring that we're not just agreeing, but agreeing with what's right. This slide highlights the key takeaways that every practitioner should remember when working with measurement systems. 1. Every measurement contains error. No system is perfect. Our goal is to understand and minimize that error as much as possible. 2. Your role as a practitioner is to quantify how much of the observed variation is due to the measurement system itself, not the process. This is essential to ensure that we're not mistaking measurement noise for actual process issues. 3. Always validate the measurement system before analyzing any process data. Jumping into process analysis without doing this is like building a house on a shaky foundation. 4. For discrete data, we must use attribute agreement analysis. This is crucial when dealing with categorical or go-no-go type measurements, where human judgment often plays a larger role. 5. Finally, always ask, does the difference matter? Just because two values are numerically different doesn't mean they are significantly different. Statistical and practical significance should both be considered. These are simple but powerful principles that can prevent costly errors and misdirection in improvement projects.